And, so I can show those, but it would be nice if people engaged and it's more of a conversation, because otherwise I get bored just talking to myself. So. All right. So let's see. I need to share my screen. Hi, Dan. Okay, can you guys see the screen now?
Yes, we can. Hi, Luis. Perfect. All right, so I guess we can get started. Okay, then. Okay.
Hang on a second. I'm just trying to arrange the Zoom thing on my screen. Okay, so this talk was basically motivated by some thoughts and conversations that came up as I was thinking about how we use models to do various things. And question came up is in science, science is all about understanding the universe and doing discovery. And the question is, how do actually models support our ability to do discovery? So, as I said, it's supposed to be more of a conversation. Yeah. All right. So, I think as many of you know, I'm interested in what I like to call the learning problem. And if I sort of go back to the beginning and say, how does learning actually happen? I guess I, go back to, I'm having trouble with the screen. Okay, there we go. So I would say, the motivation for learning is very, very primitive. It's basically you've got an organism. The organism needs to survive and thrive. So you got the principle of survival of the fittest, Darwinian evolution or something like that. And in order to, and it has to function in an relatively unpredictable environment. And so in order to survive and thrive and pass on its information, which is encoded in its genes, it needs to survive. So in other words, it needs to learn how to build models of reality, because let's say that you've got a predator, and the predator, in order to survive the predator, you need to be able to predict what that predator is going to do, or if there's a dangerous part of the environment, you need to be able to predict how to engage in that environment. So we need to build models or representations, and they need to be effective in the sense that they have to allow us to survive, and they have to be relevant, which is to the particular problems that we're trying to deal with. So we normally, I mean, this part is fairly obvious. Most people think of this, but what I think is not necessarily taken as seriously or as it should is the fact that there's a constraint on this learning process, which is our models need to be as compact as possible. And the reason they need to be as compact as possible is because you need to do computation in a sort of finite amount of time. And you've got limited, your organism has limited memory storage, computational power, limited amount of time. You need to be able to predict what the lion's going to do before it eats you. And so that model needs to be relatively simple, relatively fast, relatively effective. So this minimum description length principle I'm finding is coming up in a lot of places, and it helps to explain a lot of things. Okay, we can talk about that. So my definition of model is it's a compact, relevant description or representation of reality. In other words, it's some kind of abstraction. Okay. So how do we use models in science? You could argue that science is about learning, understanding, and discovery. And we use models for different things. So one of the purposes we use models for, which we don't often recognize explicitly, is that we use models in order to sorry, got to move this window around so it's not in my way. In order to store data or information, right? Anytime we store the data, if you organize it in a table or however we store it, that's what you would call a data model. And because the data is basically discrete points in space-time that you come in, and then you have to store and organize them somehow. You also have to decide what data to pay attention to, and so on. Then you can have a model to interpret data. So I'm going to call that a relational model. And if you're going to use that relational model to do understanding, reasoning, or explaining, you can call that a physical conceptual relational model. So there's particular attributes. And if you use it for prediction, you can call it a numerical or predictive relational model. So, but this is all about storing, interpreting, understanding, and prediction. The word discovery doesn't come up there. So the question really was, how do we actually use models for discovery? So the next thing is to recognize that any model is necessarily based on a particular representational approach. So we've got reality. We have some sort of window on reality from which we get data, and that data is determined by our sensory perceptual processes. For organisms, it's biological. For us now, we've invented new technological ways of accessing reality. And then that data is then used to build models, and that involves some kind of interpretation. As I'll argue, that's compression. And so both of these essentially involve representational approaches. So the data model involves not just restrictions based on the sensory mechanisms or the technology we have to collect data, but it also reflects choices that we make about what to pay attention to. So there's a feedback loop from the model, or representation of reality, to the representational approach used to collect data, so that if we don't actually pay attention to something or think it's important, we don't collect it and store it. So there's a loop that goes on back in this entire process. Okay. So underlying the data that we can obtain and store is a representational approach that's constrained by biology and technology, is directed by relevance or theory. We choose what to look for, what to pay attention to. And so different representational approaches result in access to different kinds of information about reality. These can make it either easy or hard to extract relevant information. In other words, the representational approach affects how easy or hard it is to extract information. The very simple example of that is if I am collecting two attributes, X and Y, over here, and the data sort of looks like this. And so I've got two classes over there, and I want to do a classification into two classes, a recognition problem. This representational approach is much more represents an approach which makes the analysis much more complicated than if I shift the origin to the center and use a polar coordinate system, r theta, to analyze the data, because then when I represent it in r theta space, it's very easy for me to do a simple linear separation of the data into two classes. So the analysis part is enabled by the choice of a particular representational system. And we'll see another example of this later on. So that's just a trivial example. As I said before, the representation needs to be as compact as possible, the fewest number of bits, because otherwise it takes a lot of compute power and storage to deal with this. And also the representation must preserve and make accessible all of the relevant information. So if you place the data into a representational framework which doesn't preserve all the information, then you've lost it, essentially, or it's hard to get at. And then, and then it's important to recognize that when we represent data, there's a fundamental paradigm that we use which underlies all of our data representations, which is 4D space-time indexing. Every data point is indexed by location in space and time, whether we pay attention to it or care about it or not later on. And we also index by some magnitude or strength attributes. And if you just go to the web page and look up the International System of Units, you will see that as scientists, we have decided that there's some very fundamental attributes that we're going to index everything by: mass, length, time, so on and so forth. There's like 7 fundamental units and a whole bunch of derived units and so on. So underlying anything we do, we already have a representational approach. And we presume that that representational approach is optimal and that it serves our purposes. Okay, and probably it does, but it's important to recognize that it may not in some ways. The relational model, the one that we care about, okay, that also is built upon a representational approach. The model is a compact, relevant description. It involves compression, right? So when we have a data set, the model represents an approach to an attempt to create a minimum description length representation of that data, something more compact, which we call compression. Right? Now we can do that compression in a lossless way to preserve information, or we can do it in a lossy way, which loses information. And my argument is that in the earth sciences, our models are usually lossy, right? We try to preserve only general information and discount very often very specific information. And therein lies one of the interesting and important differences between machine learning models and physics-based models, is that machine learning models are often built for prediction, and so they're trying to take advantage of all the relevant information in that particular context to do that task. Whereas a physics-based model might be looking for a general model that can be applied in many contexts, not specific to any particular location. So partly it's because we want to ignore or discard data errors, and partly because we really just don't know how to do the compression. So there's some language here, but anytime we talk about compression, we have to recognize that compression involves a dictionary and a set of representational rules. And we have to choose that dictionary and that set of representational rules in such a way that we get as little loss of information as possible when we do the compression. Okay. We're usually guessing, so we often throw away information that's actually important. But another way to think of this is that in learning how to communicate with each other, English has one dictionary and Chinese has another dictionary. And the choice of the dictionary in English and the ability to build words up and so on it affects our ability to represent the world in terms of words and communicate with each other. And the Chinese dictionary is far more extensive than the English dictionary. And I think Stephen once showed that the Chinese dictionary allows you to represent a lot more information than the English dictionary, as an example, right? So what we're taking is reality and we're compressing it down using that dictionary and those set of representational rules. So if there are things that we decide we need to represent, we end up having to invent new words, for example, to convey those concepts. So building a model involves compression to extract information. This involves encoding in a manner that's interpretable, right? The dictionary is a encoding mechanism, and we do it in such a way that after we do the encoding, we can recover it, we can decode it, which means we assign meaning at the time of constructing the dictionary. Okay, meaning is assigned through the act of constructing the dictionary. If I show you this object and I say ein, and I show you this object and I say ein, and I show you this object and I say ein, and I keep doing that, pretty soon you'll go, what's common about all those objects? Oh, there's only one of them. So ein means one, right? So that meaning was assigned by us in the process of constructing the dictionary. It wasn't somehow inherent anywhere. Okay. So that's important. And then by building an appropriate dictionary, you can do compact relevant descriptions. So if you design different encoding methods, you get different results. It depends on your focus, right? So there's no such thing as a fundamentally universal encoding method, or maybe there is, but in principle, any encoding method is based on some kind of concept that we're trying to represent at the time that we build the encoding. So we're trying to represent all possible concepts. That's kind of a challenge, because how do we know? So it depends on the information you want to preserve and emphasize. That encoding method is the representational approach. And I think you could argue that mathematics is in some ways the science of representations. Okay. Essentially, it's about developing different kinds of representations, each of them relevant to a different kind of inquiry. So when we want to study objects, we invent set theory. It's a particular kind of dictionary encoding method. Number theory, geometry, algebra, calculus. And the great thing about math is that every time they come up with a new kind of problem they want to study, they invent a new kind of mathematics. Essentially, they invent a new kind of representational approach to be able to allow us to study that particular thing that we want to study. In this context, I think we can recognize that fundamental to modeling in the earth sciences is graph theory. In other words, we have a fundamental representation of, we build our representations based on the ideas of objects and relationships amongst them. And we represent objects by nodes and we represent relationships by links. So it's a fairly pervasive representational approach. So here's an interesting example. Prior to Kepler, there was a very strong bias towards treating the Earth as the center of the universe. It was an Earth-centric representation of the world. And there were a lot of data collected and so on about that. And then people started arguing that no, the sun is the center of the universe, is a better representation to put the sun at the center of the universe. And Kepler studied this problem using the data that had been collected and the work of his mentor Tycho Brahe. And then he realized that the model that they were using to predict the movement of the planets was not good. He tried different kinds of circles, couldn't get the results, finally tried ellipses, and he chose a representational approach based on ellipses. But the other important thing was that he centered the ellipses around the sun rather than around the Earth. And so he ended up with a representational approach, which was much more compact. And it wasn't necessarily more accurate than the previous representational approaches, but it was more compact and it allowed you to explain what was going on in a much easier way. So again, the concept of minimum description length comes up. And it's interesting that there's actually a paper out there that, I'm not sure if I shared this with the group or not, but some people basically took a neural network which was designed to try to build minimum description length representations. And they sort of modeled the scientific process through this neural network. And they fed it the same data where the coordinates of the data were centered at the Earth. And they found that the neural network basically discovered a representational approach and said the correct representational approach is one which is centered on the sun. So this is not just something that humans do, but even our neural network machine learning techniques are able to do things like this now. So what kind of representational approaches do we use? One of them is sets. So clustering and classification is based on notions of similarity and differences. We build up hierarchical representation of the world using sets, nodes, and links. We can do binary decision trees based on yes/no questions. That's another way to do representations. So this can be used both for classification and regression. We've got directed acyclic graphs, artificial neural networks, which can be used to represent dynamics and system evolution. And then you've got physically based models, which are arguably directed acyclic graphs with some additional regularizing constraints like mass, energy, momentum conservation, thermodynamic principles, and so on added on top. Okay. And the nice thing about physically based DAGs is that you can do causal relationships and study how they control the evolution of the system. So just some examples of different kinds of representational approaches we used when we tried to do our analysis. Okay, so what's the problem? The problem is that the representational approach that we choose completely, and I underscore completely, determines the questions that you can ask, the analyses and inferences that you can perform, and the answers that you can obtain. Okay. And that might seem like a very strong claim, but it's actually very directly related to Gödel's theorem, which basically says that anytime you set up a formal system, any kind of representational approach, that representational approach will not be able to access all truths. In other words, all representational approaches are essentially incomplete. Okay. So let's take an example of that. Let's say I'm trying to study a watershed in hydrology, and I use a spatially lumped 3-store conceptual rainfall runoff model to study the system. What's the question I'm trying to answer? The question I'm trying to answer is, given some information about rainfall and potential evapotranspiration or temperature, what is the likely flow in the river going to be tomorrow or a day after or something like that? Okay. So the question is completely determined. Those are the only questions, those are the only kinds of questions that I can ask, and those are the only answers that I can get, and that's completely determined by my choice of lumping and et cetera, On the other hand, I could choose to build a spatially distributed model, fully 3D, and now I could still try to answer the same question, but I can also answer other questions or ask other questions or receive other answers, such as how is soil moisture distributed in space and time, how is it going to evolve, and so on and so forth. Right? So the representational approach completely constrains or determines what I can do in this context. Similarly, if I put in a neural network, which is not constrained to obey conservation principles, the questions I can ask and answer are informational questions. They're not related necessarily to mass or energy or things like that directly, but they're basically saying what informational strength relationships exist in these data sets. Okay. So 3 different representation approaches, 3 different perspectives on the same problem, the same reality. So we're trying to map from reality to data models. This mapping involves representations. All representational approaches are fundamentally limited by what can be represented. In other words, they predetermine what we can represent. They are priors, they're choices about what we can learn. And so that brings us back to the same question. If what I can discover is fundamentally predetermined by the representational approach that I choose, how am I going to do discovery? Because sort of almost by definition, discovery is about learning something that I don't know yet, right? So you can do a sort of a limited kind of discovery within the context of that representational approach, but you can't really step outside of it easily. There's another related question, which is how much of the information in our models actually comes from the data and how much comes from the representational assumptions that we make, right? To what extent does our decision at the end of the day depend on information in the data, and to what extent does it depend on the choice of how we process that information? And that's an interesting question for us in information theory, and modeling, because we like to believe that the models just compress and represent all of the information in the data. And I'm kind of arguing that no, they don't necessarily. They're actually adding information to what's in the data, and the kind of information they add then determines the decisions that we make. So I've got some examples to illustrate, to talk about this point. I'm going to talk more about how true discovery can happen. But I actually think this other conversation about how much of the information comes from data and from how much from the model is an interesting conversation. I'm happy to talk about that also at the end. I don't have slides on it necessarily. So I think that one partial way to get around this limitation of any specific array is to use multiple representational approaches. In other words, you put multiple perspectives on the problem, you try to study what each one tells you about what's going on, and then you try to look, you read between the lines, so to speak. You try to look at the gaps. Now, this kind of begs the question as to whether or not there's something that you might call a master representational approach. Some representational approach underlies all possible representational approaches, and I don't know what that is, but I'm very curious to see what you guys think about that. And if we can make some progress towards understanding what that is, I think that would be very interesting from an information theory point of view. But if we take a multi-representational approach, that's basically saying, let's approach the same problem from many different perspectives, recognizing the limitations of each perspective, and then somehow try to read beyond that. So the useful metaphor here, one useful metaphor here, I think, is the blind people and the elephant, where I dug out this poem that was written by John Sachs, who says it was 6 men of Indostan. I can use this because I'm from Indostan. To learning much inclined, where to see the elephant, though all of them are blind, that each by observation might satisfy his mind, observation being his perspective, their perspectives. And it goes on, there's a bunch of verses. In the end, it says, and so these men of Indostan disputed loud and long, each in their own opinion, exceeding stiff and strong. Each representation approach makes very strong assumptions and proceeds from the assumption that it's correct, right? That's how we proceed in science. We make a hypothesis and we proceed from the assumption that either that hypothesis is right or wrong, one or the other. Though each was partly in the right and all were in the wrong. Okay. So every representation approach is going to be limited in some sense. Luis and I and Laura Condon have just submitted a paper to WRR on this, and you can go in and access it, the preprint from this link. So the problem that Luis worked on for his master's thesis, and fortunately Luis is here so he can answer questions that I may not be able to, was how to model stream flow across the entire country of Chile. And this picture is just to show you that Chile is quite a large country in the sense of it's a very long country. It's basically as long as the United States is wide. So there's a lot of diversity there. And these pictures just show you some of the huge variety of hydrogeoclimatology, climatic diversity across the country. So here's the Americas. Here's a map of Chile, which shows basically average annual rainfall, where you can see it's very wet in this sort of central, south central region and dry in the north. So the north itself is very arid. You've got the Atacama Desert, which is the driest desert in the world. There are even places where there's been no rainfall recorded for more than 25 years. In between, you've got highly variable conditions. It only averages about 175 kilometers in width. You've got the Andes Mountains, one of the highest mountain ranges. And you've got another parallel mountain range closer to the coast. You've got steep valleys, you've got high slopes with short times of concentration. So all in all, fairly challenging. And then in the south, you've got a very wet region where you've got more than 5 meters per year of precipitation. You've got lakes, you've got permanent ice fields, and so on. So huge diversity. And Luis accessed there's a data set called the CAMEL CL data set, which basically is like the CAMELS data set in the US, but created for Chile. Okay. And it's set up to basically try to understand the rainfall runoff problem, modeling problem. So Luis applied three complementary representation approaches. One is a physical conceptual model, GR4J. Okay, it's based in a lumped water balance model, mass flows, with energy used to affect evapotranspiration. The second one was an LSTM, which is a classic machine learning directed acyclic graph, recurrent graph network, which doesn't represent flows of mass, at least unless you regularize it, to basically represent flows of information with memory about information. And then the third approach was a random forest or database decision tree representation, where the focus of decision trees is on asking questions like about feature importance, what things are more important first and then come second, and so on and so forth. So three related but somewhat different perspectives on the same environment to model the same situation. So here's a plot showing the performance metric. I think it's KGE on the x-axis, and so better values to the left. So we've got a whole bunch of catchments. Luis, how many catchments were there? 600 or so?
322, because the total number is, yes, because we reserve a special number of catchments that were used for kind of auto sample.
All right, yeah. So total there were some 600 or 700 catchments, but 300 and something were used in the study. And so what you're seeing is a distribution of performance across Chile. Okay. The blue line represents the LSTM network approach. And you can see that in the majority of catchments, the LSTM gave the best performance. This is very consistent with Freddie and Gray's work and Xiaoping Shen's work in the US. Okay. The green line is the random forest, and the red line is GR4J. So this is the color coding scheme I'm going to use for all of this data. What's interesting to see is that for the catchments where performance is very good, all three representation approaches do almost equally well. In the intermediate range, the LSTM does better. The GR4J isn't the best anywhere in this way of looking at the data, but you notice that there are some places where GR4J actually does better than LSTM. Now, of course, it's quite possible that something went wrong in our construction of LSTM, but we followed all of the recommended strategies for building these three models. In other words, the LSTM was built based on best practices for LSTMs, GR4J based on best practices for physical conceptual models, and random forest, and so on. So this suggests that there are places where, even though all three models had access, representation approaches had access to the same data, that GR4J was somehow able to either access that data in a better way, or, which is unlikely, or more likely, because it involves regularizing assumptions, it was able to use that information provided by those assumptions in order to get better performance. If you look across the country, red, blue, green dots represent which model was the best in any particular part of the country. You don't see any spatial pattern, clear spatial pattern, in terms of just looking at it like that. However, if you take the data and you represent it in this way, notice that our analysis, the way of analyzing also represents a kind of choice about representational approach. So here's my map. The colored dots, green means good performance and red means poor performance. You've got the Atacama Desert in the north, you've got glaciers and lakes in the south, you've got relatively wet in the middle there, and then drier and steeper slopes above that. If you plot the results by latitude and then run a 15 catchment moving average through them, you see this interesting pattern where I've drawn a line at metric of 0.5, meaning I'm going to say that better than 0.5 is good, worse than 0.5 is bad, and negative values are really bad. You'll see that in the central region, all three models perform pretty well. In the very south, you get declining performance with the physical conceptual model, and this makes sense because GR4J doesn't represent glaciers and lakes explicitly, so you can't reproduce those kinds of behaviors, but the machine learning models somehow managed to do it. In the north central region, all the models perform poorly. This is the region that's characterized by rapid elevation changes, short concentration times, great aridity. And in particular, the random forest is really poor. And on further analysis, one of the reasons the random forest performs very poorly is because when we're trying to build memory into our machine learning models, the GR4J and the LSTM have this internal cell state which allows it to track memory over long periods of time. Whereas the random forest, in order to track memory, you have to give it explicitly the past number of lag times of data, and that represents the memory. And if you exceed this for longer than about 32 days, the computational burden on the random forest becomes too high, and you're just not able to include explicitly. I mean, there are other ways we could try to get around it, but in this study, we were just using daily lags. Okay. And so something to do with memory is going on in this north central region. And then you go in the north and you see the random forest and the LSTM get better, but GR4J doesn't improve. And this is arguably because GR4J was developed for France, and this is the desert Atacama area, and there's some processes that are just not being properly represented in the GR4J model. For example, it might, and there's also some problems with the data set. The data set doesn't really give us any information about groundwater processes and so on. Now we can change the representation, and instead of plotting it by latitude, we plot it as a function of aridity. And now an interesting thing emerges, because you can see directly a log linear dependence on aridity for all three model types. So all three model types have access to the same data set. As we go from energy limited to water limited, as we get drier, performance falls off. And this strongly suggests that the data set is incomplete. It's not sufficiently informative. It's informative about wet conditions or energy limit conditions, but it's not contain the variables and the information that we need in order to do a good job of modeling rainfall runoff processes as in regions as they get drier. And in drier, hydrologically, we know that the dependence of streamflow on precipitation becomes less. And it's affected more by things like evapotranspiration, groundwater storage, and so on. Okay. You also notice that the LSTM performance is more unstable than GR4J. GR4J has more of this trend with less variability around it. So the LSTM, which is less constrained by regularizing constraints like physics and so on, when it performs well, it performs very well, but it can also equally perform worse. So there's a lot more variability. And there's this region between aridity index between 1.5 and 8, where the random forest does much worse, and we explained that on the previous slide as having to do with the memory length. So we kind of know this, but this study very clearly points out that the CAMELS data set is informationally biased, which means that it makes it difficult to learn certain things that we would like to learn. If you look at the random forest and you look at the first split, it becomes very clear that aridity is the strongest controlling factor on what's going on, followed by precipitation. If you look at the feature importance at the first split, you see that in the forest, the number of times a particular thing is chosen as the first split, aridity is the highest. Most of the factors have to do with precipitation, but there is a couple of factors that are interesting. Vegetation cover plays a role, and which is not necessarily information that can go into GR4J. And there's a dependence on seasonality, which you can say is related to memory, which clearly comes up over here. It's not as strong as routine precipitation, but it's important. Going back to memory timescale, if I plot those cumulative probability plots for the random forest, and I vary the amount of memory, that the random forest method has access to, you can see that so we already know that arid catchments are down here, wet catchments are up here. We can see that as we go from 2 days up to 32 days memory, performance keeps improving, but it becomes less and less and less. The marginal improvement is smaller. Okay, so clearly memory plays a role. If we do the same thing for the LSTM, we see it, because in the LSTM, we're actually able to feed in memory up to 365 days of past data. So once again, there's the 2 days memory. There's a cluster, which is 8 to 128 days memory. And then you get this set of curves, which is 270 to 365 days of memory. And so you can see whereas this additional long-term memory doesn't play an important role in very wet catchments, it actually plays a very strong role in the drier catchments down here. And if I take this curve and I transfer it over to the random forest curve, you can see that it's very suggestive of the same thing, that potentially if we were able to feed in longer memory into the random forest, we could also get something like this kind of improvement in its performance. Another thing that Luis did was he kept some of the catchments out, did not use them for model development, and then he used them for what you would call an out-of-sample testing. So all of the results we showed so far were evaluation period results, but on a different time from the same catchments. And these data are now for different catchments altogether, right? So it's a spatial evaluation test, a much stronger test in some sense. Yes.
Leila has a question.
Leila, yes. Sorry.
Thank you. In the previous slide, could you please explain why the area is smaller as the memory is longer?
Sorry, what was the question again?
The question is that I noticed that the area is smaller as the memory in days is increasing.
Which area are we talking about? The area to the right of the curves?
Yes. And it is in the legend. So I am reading in the first graph. So the memory 2 days, the area is 0.
Sorry, I didn't define that. The area is the area to the right of that curve.
Okay.
It's just a statistic of performance. The small values mean better statistical overall performance.
Oh, okay. Thank you.
Does that make sense? Yeah.
Yes.
Okay. So same curves. So here are the curves for LSTM and random forest on the in-sample testing, meaning it's still evaluation period performance, but on the catchments that were actually used to develop the models. And then when the same, when those two models are now, and when these two models are applied to another set of catchments, which has a very similar distribution of samples, we find an interesting result, which is now the the LSTM is not necessarily better than the random forest. Okay. So when we're testing in sample, LSTM looks better, but when we test out of sample, both models perform more or less equally well. We cannot run this test for GR4J because GR4J has to be calibrated individually to each catchment, right? So when we talk about LSTM and random forest, we're talking about one model built for the entire data set. So this tends to suggest that there's some overfitting going on with the LSTM because it doesn't have enough constraints on the functions that it can fit doesn't have regularizing constraints, that somehow it may be a little bit too optimistic a representation of performance, or how performance would be if you were to apply the same model to ungauged catchments, right? So you could say this is like the prediction in ungauged basins test. So from this point of view, both the machine learning models actually perform more or less equally well when tested out of sample. Just to give you some idea as to what the hydrographs actually look like as hydrologists. So here's a catchment where the LSTM did very poorly up in the Atacama Desert. The blue line is the LSTM. And you can see there's no regularizing constraints. It's not able to use the information. It's just really wild all over the place. Here's a catchment also in that region where the GR4J is pretty good at peaks, but not so good at recessions, whereas the two machine learning models are actually following the recessions much better. And then here's a catchment in the relative area where you can see that all three models actually do comparably, remarkably well, perhaps with some question about the recessions here for the GR4J model. But you can see that even with access to the same data sets, the method used to do the analysis results in quite different kinds of representations about what's happening in the system. Okay, so in conclusion, the database model, LSTM provided the best overall predictive performance. We think it may be prone to overfitting. It's a little more difficult to interpret what's going on inside the model, and the results can be more unstable. The database random forest is useful for enabling discovery because it asks questions like what's the most important thing in partitioning the data into sets. We also found that it tends to generalize better to new samples. This is something that a lot of people have been reporting, that the random forest is like your first go-to method for analyzing data. There is, however, a limitation on long time lagged sequences and studying long memory processes. And so we need to come up with more creative ways of representing long-term memory, which can then be fed into the database random forest model. And then the physically based GR4J, in some sense, provides more robust results because it's providing physics-based regularization, which involves information that's not in the data. Ultimately, the argument is that this is a sort of it's a sort of a crude example of how using multiple representational approaches supports a kind of discovery or different kind of discovery than if you were to use a single approach by itself. By comparing one to another, you can start to learn things that were hard to learn by just using a single approach. And somehow we get a more comprehensive overall picture, more in-depth investigation, and we're able to reveal things like limitations of the data, for example. So at this point, I just got a few more slides. You might ask the question, what's different between a multi-representational approach and a multi-hypothesis approach? In science, people have been saying you have to use a multi-hypothesis approach, and Martin Clark has been pushing for a multi-hypothesis approach in hydrology. So here's a question for general discussion. Do you think multi-representational approaches is the same as a multi-hypothesis approach, or are they somehow different? I'm curious what your thoughts are about this issue. Anybody?
Well, I have my opinions. I don't know.
Okay. All right.
So
you're entitled to have an opinion.
For me, just multi-hypothesis is just when you are already defining a representation and you are trying to change a specific hypothesis or process inside of that. So this way you are testing each one of these. Okay, in some situation could be better, and you are trying to learn under what condition each one is better. So you're changing just kind of one part of the representation, but the overall picture or overall representation is the same.
Okay, So you're basically arguing something similar to what I think I'm saying, which is that representations and hypotheses represent orthogonal perspectives on the modeling problem. Within a particular representation, you can test many different hypotheses, or you can have a hypothesis and you can use many different representations to study or test that hypothesis. That's the claim over here. So they're sort of orthogonal. So you could have a single representational approach on one hypothesis, very common, right? How we build models. You could have a single representational approach in many hypotheses. So the fuse method or these methods for building modular modeling systems in hydrology basically make an assumption about a representational approach, and then they allow you to test many different hypotheses within the context of that representational approach. Oops. You could then conceive of a single hypothesis and study it with multiple representations, but it would seem to me that the most general and most powerful approach would be to use multiple representations and multiple hypotheses, so that there is actually something fundamentally bigger than the idea of a multi-hypothesis approach. Although you could argue that a representation is a kind of a hypothesis, and I wouldn't argue against that. I'm just trying to reflect how the term hypothesis is colloquially used in our language. More generally, I'm just saying use as many different perspectives on the system as you can invent or come up with. Okay. This is just what I say when I give this talk to people at the U of A. I say, oh no, what I wanted to say was, since I prepared this talk, I'm seeing more and more examples of how our adopted representation approach affects what we can learn. So I've been reading papers recently about machine learning, where people are showing that convolutional neural networks, when they process the images and they use them to classify objects like cats and dogs, they tend to rely not the way that humans do on the shape of the cat or the shape of the dog, but they tend to rely on texture information. And so they're very subject to adversarial attacks because you can put a little blue dot in the corner of every dog image and a little green dot in the corner of every cat image. And it doesn't matter. As long as there's a blue dot, it'll say dog. And as long as there's a green dot, it'll say cat, because it's learned that that's the best predictor of dogs and cats in the images. Or you can tint one green and tint one red, and it'll, every time it sees a green tint, it'll learn one thing and red tint. So it doesn't necessarily obey the same perceptual and conceptual processes that humans do. So people have been showing that if you process the data to reduce or remove texture information, then you can force the convolutional neural network to learn to classify based on object shapes rather than textures. And so that's a different way of putting priors on the representational approach. So I'm seeing this coming up over there. And then arguably, every time you take the data out of your model and you analyze it, if you plot it as a scatter plot, that's one representational approach. If you plot it as residuals, that's a different representational approach. If you plot in a log scale, that's a different representational approach. So arguably, we already use this concept of multiple representational approaches as windows on reality to already do our analysis. I'm just suggesting that we need to take that idea and push it all the way back to the very beginning where we start our analysis, not just at the end. So just again, back to the blind people and the elephant, each in their own opinions is exceedingly stiff and strong. They each was partly in the right and all were in the wrong. My perspective now is that, information theory provides a useful approach, physics provides a useful perspective, machine learning provides a different useful perspective. They're all somehow related. But if we were to try to argue that one is the best approach or the only approach that we should follow, we probably would run afoul of this this assumption that we had the correct approach and make it difficult for us to actually learn what was actually going on. So basically my message to everybody is on my learn data science, machine learning. Okay. The idea, I think, is that in the future, and that's why this group exists, is that science will be driven less by heuristics and more by a structured approach based on understanding the nature of information theory, machine learning, how we learn, and so on. So we're trying to map from reality to data to models. Building this mapping unavoidably involves representations. All representations are fundamentally limited. This is just a summary. So the question back still is, how does true discovery happen? So how do we actually discover things? I don't think that the multi-representational approach is a full answer, but it's hopefully a partial perspective on how that can happen. And the related question, which I didn't talk about, is how much of the information in our model comes from the data and how much comes from the representational assumptions. I think this is a hugely important question for us to tackle as the information theory group. All right.
Okay, first of all, I think the time shift screwed my calendar.
Oh, sorry about that.
So I'm going to have to watch your presentation recorded version because I thought it was just starting at now.
Sorry about that.
Yeah, and you mentioned the other day you might be driving today, so I thought that you might be in the road. Sorry.
No, I had planned to be in this meeting from 1 to 3, but it turned out it's 12 to 2. So sorry, Hoshin, I will have to watch this.
No problem. The basic summary was that, we've talked about this before. The representational approach completely determines the questions you can ask, the analyses you can perform, and the answers you can receive. And so it was motivated by the question, if that's true, then how do we actually do discovery? And the proposal on the table is that I don't have a full answer to this clearly, but that we use multiple representational approaches because each representational approach helps to put a different perspective on reality, like the blind people and the elephant. And then I just showed some examples from the work of Luis, where he applied this approach to Chile and applied a physical conceptual model, an LSTM, and a random forest model to the same data set. And we learned interesting things that we think we would not have been able to learn by just using one approach by itself. Okay. That's sort of a nutshell summary.
Can you hear me okay?
Yes.
Okay. Yeah, I really like the way the results were mapped differently, with energy constrained and aridity constrained. Those were really, I guess, when you pose the question about really, is there a difference between multiple hypotheses and multiple representations? I couldn't tell the difference. And but I think if you go back to the cartoon,
sure.
I'm wondering because all of them are they're using, they're touching the elephant, right? So I guess maybe the analogy would be if they're not all, if one of them is seeing and one of them is smelling or something, and I don't know, like, to me that's like a different way that maybe there's multiple layers of representation, and I think the really powerful one that you all showed is just the different way you map these results to to different parameters in different spaces, and I really like that.
You're talking about
thanks for the presentation.
Yeah. So here we're mapping it by aridity versus mapping it by latitude and so on.
Yeah, and the more the more those sort of mappings, the more people and the more senses you're using to explore Correct. The elephant. I think that I really like that analogy.
Actually, there's Vic Baker heard this talk last week, and he said something interesting. He said that he thought the better analogy was not the blind man and the elephant, but the drunk under the light post searching for his keys. Where the policeman comes along and says, "What are you doing?" "I'm searching for my keys." He says, "Why are you looking under the lamppost?" He says, "Here's where the light is." So there's probably several representational metaphors, which could be used to put different perspectives on the same problem. The way you're looking where the light is sort of like, well, this is all I can see. These are the sensory tools that I have to try to view reality through, which is why I think mathematics is so interesting, because it provides you with so many different representational approaches to trying to study a problem. We have to affix the lamp to the drunk's head. There we go. Take the lamp around with them.
It kind of makes me remember another joke from one professor back in Colombia that said that that when you turn off the lights, again, like the post example, if you don't turn on the lights, you hit the post. It's like using models without physics. It's hitting post every time. And then you have to turn the lights. It's like, okay, here's where data is. It is important to have lights.
Yeah.
And find spots.
But you know, more and more, right? More and more, I just feel like these debates between physical scientists and machine learning people about, I just sort of start to become boring, because they're like they're each trying to look at it only through their particular rose-colored lenses, instead of asking, oh, what are you able to learn that I'm not able to, you know, and which is a much more interesting perspective approach. You know, the generative adversarial thing that we were talking about, Praveen, that we need to bring to this whole discussion. Longshu.
Hey, thanks so much for the opportunity to speak, like, one of the person who doesn't speak so much. First of all, I really like the story, everything. I think it's a really nice presentation, very nice analogy. Yeah, it's great. I have actually several points I want to bring up, maybe just for the sake of discussion. I think we have a smaller group here. So first one, I think you mentioned about this, the abstraction compact. When you do modeling, you basically, trying to make things compact to squeeze out the core information, which is basically building a model. Trying. Also, you mentioned about the discovery, which is unsupervised learning, if you can call it that way. But what I kind of want to say is it's always going to be a balance point, right? There's always, if you want to really do the classification, you can argue to say if you can put the individual one as one group, that's a classification. Or you group everyone together, just a single group, that's another classification. So the modeling part is actually trying to find the most optimal bargaining point that you have carved this data in the space in a way that they capture certain features. It's also not fully represented or oversimplified, which is kind of a tipping point in the modeling process. So I understand that you mentioned that minimization is very interesting, but I'm not sure the minimum the minimized model is the best model. That's just my thought for exchange. That's number one. So number two is you talk about how to make.
Can I just respond to that before you go on?
Yeah, please. Yeah.
Yeah. So I just want to mention that I emphasize compact, but I also emphasize relevant. Right. So the representation depends on the goal that you're trying to achieve. And so putting all the things into one cluster might be relevant for one particular task. Leaving them all as separate might be relevant for a completely different task. So.
Yeah, I agree with that. Okay, I think I think that's I agree. Yeah, I think that's you talk about relevant. I'm trying to talk more broadly. Just think about everything else. To talk about the pure representation abstraction by itself. Yeah, I agree. Yeah, fully agree. Then I think you also talk about this multiple hypothesis versus multiple representation approach. I really like the multiple representation. But for me, there's one question came to my head isn't hypothesis, the formulation of hypothesis is also dependent on some representation. It's like, you know, asking the question whether the mechanic wave exists when there's no media. So something like that. So to my head is the hypothesis formulation is more or less also contingent on the representation. So I think they're kind of I don't know, they are mutually independent, or they are kind of it's not very easy to separate them. That's my, yeah.
Yeah, I agree. That makes sense, because you can have a hypothesis and then you can choose your representation conditional on your hypothesis. Or you can have a representation and you can choose your hypothesis conditional on your representation. So it's sort of a chicken and egg problem in some ways.
Yeah. I mean, I can also give example from, like, you have to do the, let's say, the simple hypothesis testing for the linear regression or something. You formulate that hypothesis in such a way because it's testable. If it's not testable, you probably don't want to formulate hypothesis in such a way. But just for argument, then I think the last 2 points, maybe it's more interesting. Is one is about this multi-hypothesis also continuous saying. You know, I really like the work you show, this comparison between LSTM, random forest, and the physical model, and you see the benefit when you look at this same problem from different presentations. But I just want to raise one point. You know, if you think human brain as probably the most complicated or sophisticated or the most advanced neural network, you know, for the intelligence, but given the same representation, different people may come up with different interpretations, right? You have the same graph in front of different people. When they look at it, they're trying to extract the features from it. So there's also diversity among people based on the education background, their disciplines, many different factors in. So I think maybe there's also something about the human consciousness as a concept in interpreting this the overall representation. Just not only representation itself, it's also another layer behind it. It's the interpretation of representation. That's another one. Yeah, and last one, you mentioned about how to do discovery. I fully agree, you know, for your analysis based on the model, the limitations. But in science, I think in many the field of science, sometimes people always call about serendipity factor in discovery. Some people
serendipity. Okay.
Yeah, serendipity. Sometimes people just step on something just by accident and made a discovery. So I don't know whether this falls in anywhere the presentation you trying to show today, or there's something extra people. I know it's difficult to consider. It's totally accidental, but that's actually happened so many times in the scientific discovery, right? So that's all my comments. And last one, if I could, it's just about the memory effect in random forest. I wasn't sure exactly how it was treated, and how do you think the treatment of memory effect in the random forest versus LSTM? Because the structure of models are different. So that's probably a little more detailed question about the exact treatment, the technical question for the memory effect. The conclusion of my question.
That's a great question. That's a great question. Let me just say that to your serendipity comment, there's this idea that people say that chance favors the prepared mind. So maybe having multiple representations on reality is kind of like the prepared mind. I'm not sure, but it's something we're thinking about, right? But I completely agree. Discovery is very often driven by chance. But it's sort of like if I don't have the tools to recognize that something interesting or weird is going on, then I might have the chance, but it doesn't actually happen because whatever happens, I just ignore, or you know, it just flows off me like water, or it doesn't stick, right? So this is an interesting point. That's what thinking about.
Yeah.
Let me throw. Yeah.
Sorry. I just want to follow on that because I agree, but I think also, you know, this may also have some context in the data. For example, the black swan phenomenon, right? People have been, yeah. So I think you got it. Okay.
But it's interesting because what some people will do is they will take the outliers and they will call them outliers. They will say there's a problem with the data.
Yeah, that's happened also many times.
Representation.
Yeah,
right?
yeah.
And, a different representation would be to say, oh, these are the most interesting data points.
Yeah, you can view in that way also. Yeah, agree. Yeah, yeah.
I'm going to let Luis answer your question about the memory stuff.
Thanks so much.
Yeah, no, the memory for LSTM, really what we are thinking there, we are using the same word as memory, but really for LSTM, we are talking about the sequence time that's inside. So it's the number of time that you are doing the recursive process inside of LSTM. So the number of time in some way is the memory that is, or how many days do you need to estimate the state now. So in some way it's kind of memory. And for random forest, given that random forest was kind of divide and conquer, doesn't have any state inside. So we decide that, okay, we are going to add memory using the daily information from the past. So this is the number that we have there.
Yeah, okay. Thanks for the clarification. But I think I'm just want to talk about exact point because the configuration of random forest doesn't really treat the previous state or memory in a memory way. They just go again to this divide and conquer approach. But on the other side, the LSTM has its internal structure. It can manipulate actually to configure the sequence. So in that sense, I think the memory effect has been considered both in two models, but because two models have different representations, their true information or true meaning between the two models may not be the same.
Yeah, completely agree. Yeah, it's true.
Other comments, thoughts?
If I may ask one question, and I want to add one comment to what Longsu was saying. In the blind man in the elephant problem, I guess the issue is that everyone is defining way too fast and claiming discoveries way too fast on what they can see. But we are like not saying, okay, we are looking at something that is probably larger than what I can perceive. And okay, I can give a description of what I can see based on my coordinates. And many other people can claim different descriptions of what they can perceive. And then we can sum up, or I don't know if actually summing up will help for the bigger picture, but at least we will say, okay, we are looking at a whole instead of different little things and then putting all together. But I don't know if jumping too fast into discoveries and many discoveries is what is actually preventing us from making actual discoveries.
Interesting, because that suggests that that sometimes you need somebody to look at the same problem from a different perspective in order for a discovery to happen, right?
Right.
I mean, we see lots of examples of this in science. But I'm also intrigued by the notion of that in order to build a representation, I have to build a dictionary, right? And the choice of dictionary sometimes is so buried that I forget that the dictionary that I built, the encoding rules that I built, fundamentally encoded certain assumptions right at the very start, which makes it very difficult for me to even recognize that I'm missing something important, right? There's a lot of buried assumptions or implicit assumptions all the way back at the very beginning of how we build a dictionary. And an interesting example from physics is that physicists have now become more or less resigned to the fact that in certain contexts, light should be described as being waveform, and in another context, it would be described as having particle attributes. And now nobody claims that one is right or wrong. They just claim that both are true, depending on the context, which is like saying depending on what problem I'm trying to study, right? The relevance problem. So could we argue that there's something more fundamental than light and particles? Maybe. I don't know what that is. And that would be akin to asking, is there a master representational approach?
Right. When you're saying that, I kind of think about how do you know that you did not know something?
Good question. I like that one. How did I know that I did not know something? Okay.
Yeah, because then you can step on by serendipity on something that you that is maybe not something that you are not discovering for the first time.
Sure. If you don't mind,
yeah, sorry.
Go ahead. Go ahead, Longshu. No.
Yeah, I just want to, jump in to comment on that Leah's point. I think probably we cannot know the answer to that one. We don't know, but actually that's how the discovery happened. I think if you watch carefully in the disciplines like in physics, before people came into quantum mechanics, people thought they have the complete knowledge in the classical world that everything was there, except for that two weird phenomenon people couldn't understood. And looking for the ether. But just because it's two outliers, as what Hoshin said in the beginning, it led to a great discovery. So it's something don't know until you come to it, and you factor it back into a theory and improve the model. So the model will continue, evolve, and better itself. So by now, we probably all accept quantum physics, probably the most proved theory that governed the fundamental operation of the universe, but maybe it's still incomplete. Someday down the road, we'll discover something that we couldn't use the current theory to contain. Then we modify our theory, we change our model. So that's my reaction to the Leah's question.
Some comment related with that is that, at least for me, or what I have learned here, is that generally when we see something that we believe is an outlier or is random, or okay, we said this, we have this error, and I'll say we assume this is an error. Sometimes there's something, really this error is just because there's something that you don't know. So sometimes we are just we are taking very simple assumptions and saying, okay, this is just some errors. But normally the discovery is happening is just there. Is that we assume that is something is just an error, but really something else that we are not considering that makes sense when you assume that.
Yeah, I guess building on Luis' comment, sometimes it's a matter of the scale at which the process has been explored. And so, for instance, when I am working with high frequency data, probably many people discard some of the data just because it does look noisy, but it's probably not noisy. It's just that you are not looking at the scale that you should be looking at to make a discovery in another scale. So yeah, actually, I have a question for Hoshin and for everyone. In my research, I use a structural model as a representation for causal discovery. And how do you think that causality can play a role in the machine learning discovery? Is something that if we add causality, we may tend to see the bigger picture of what is going on, because currently our models are basically physical models or data models, but we tend to forget that each variable can also tell us the story about the system in which the processes are occurring. So I guess adding causality to our modeling is what is missing somehow.
So here's a question for Praveen, I think. Your question, Leela, made me think of causality, causal relationships as being possibly informational and possibly physical. right? And what Praveen and your group has been trying to do is to try to break down this separation between what is informational, which we tend to call correlations, and what is really physical, which we tend to call causal, right?
Yes.
But I could cause you to go out and buy a book by telling you about it, and that's informational, right?
Right.
So it's an interesting question about the relationship. I don't know if Praveen or Allison have a reaction to that.
I mean, for me to react, I think I am more and more reconciled to the fact that any dependence can be characterized as informational with caveats, right? So is correlation, I mean, I don't know why correlation would be informational. I mean, basically, if the sun shines, the temperature goes up and I don't know, the humidity goes up because there is more evaporation. So there would be a correlation between temperature and humidity, but it's caused by an external driver called the sun. And so you could have the correlation structure coming because of something else driving, which is the sun. I can call that causal in some ways, right? But you could also look at the dynamics, and if you look at the turbulence rate literature, basically the scalars are transported away from a surface in a well-developed framework called an ejection sweep mechanism, where you have a turbulent structure which is essentially periodically pushing away scalars, not continuously. It's not a continuous process, and therefore you get these bursts in the process, and that is very much dependent on the structure of the roughness and buoyancy and other factors, and so the temperature would play a role in this. I think it's but how things happen versus how one influences another, I think are probably different questions. And I think when we're talking about causality, the causal, I mean, I'm operating under the hypothesis that anything causal is affected through information flow. If I get you to buy a book, that's going to be an information that is sent from me to you and saying, hey, this is a good book and here are the good things, and that may result in an outcome in there. So even when you're looking at physical processes like Leela is looking now, or Allison and Pishi looked at, we assume that when 2 or 3 variables interact or more, it's through some mechanism of information. I mean, that's why I'm talking about fluctuations being the bearer of this information, right? If something changes, something else changes in there.
That makes sense. So what we're calling a physical causality is really just a higher level view of something that's more fundamentally informational, I think is what you're saying.
That's what I think a lot of my hypothesis is in there, right? I mean, so even the laws of conservation of energy and so forth, or momentum, what makes this conservation happen? So whenever we say laws, the purpose of the use of the term laws is don't question this. It is given, it is as is, right? Force is equal to mass times acceleration. Don't ask why, right? Because that's the law. But if you ask why is that the case, then again, you immediately get into relativity and say, okay, there is an explanation for why force is equal to mass times acceleration. So the laws as we know it break down under explanation of why some things are happening. But if you don't want to dig deeper, those are the laws, right? And so these are conceptual mnemonics to operate at various levels, right? So if you're not dealing with quantum or relativistic, I mean, Newton's laws are there to characterize that. If you are dealing with thermodynamics and you don't want to deal with statistical behavior of each molecule, then the thermodynamical laws are there. I mean, basically they shield you against asking any more detailed questions. But those detailed questions can and should be asked if you want to get to the bottom of it. So I'm not too enamored by the idea of laws as a stopping point for us to think about, right? Because basically they stop you from probing deeper in there.
Allison, I saw you turned your mic off.
Yeah, I have a related question, definitely not an answer, but just one thing that something that Praveen said made me think of is that one of the things that I find difficult when I try to expand the notion of causality outside of like the time series data and directed graph type of stuff that we've done is the idea of something could cause something to stay the same, you know, so there could be a kind of like a causal stability where, you know, I'm holding this cup up and it's staying there, you know, and it's not moving. And that's because I'm like exerting this force on it. And, you know, it just doesn't seem to translate to what we're talking about when we talk about causality is that, well, we really saw the causality when I put it down and it changed. So it's like, you know, a change in one thing causes a change in another thing. And we get this propagating sort of change. But then it's kind of like within the moment that something is the same, that, you know, there's no possible way from your data to infer causality, which I think is kind of a strange thing to think about.
Yeah, but that's a very good question, Alison. And I think the answer is pretty much tied into this whole causality thing, which is counterfactual. So if you're holding the glass and if you were to not hold the glass, what would happen? It would not stay in place. And therefore, you're holding the glass is a causal factor for the glass to stay.
Right.
So
yeah,
the whole
yeah,
counterfactual story is tied to the causality story.
Right. That's a good, you can make your time series be a series of counterfactuals of different realities of whether I was holding it or not holding it and whether it was up in the air or not up in the air. Yeah, that's a good answer to that. The kind of related thing that I wanted to, I think this relates to question 6, which I think is a really interesting question that I've been asking in sort of a different way, or just using different and probably less articulate language. But the way that I see question 6 is, how do you disentangle the input or source data from the model structure, or what you're calling the representational assumptions? So how do you kind of separate what information is coming from where? Because the model structure, like you said, is just completely restricting the questions you can ask and the possible things that you can get from a given set of input data. But then the input data itself is also, it's giving you a lot of information about the system state, and it's the way that, you know, the model, it's what the model has to use to get the answer. And so this is kind of a question that's related to model predictive performance, I think. So the example that you talked about with the aridity conditions, I think you mentioned that, you know, the models perform worse in high aridity conditions, and that is because the input data doesn't contain the necessary information to make a good prediction. So that case you're saying is because the model has poor performance because the input data is not informative of the output data, right? So that's like one possibility, but then another possibility I think would be that the input data does contain the relevant information, but the model is just unable to read it for some reason. So the model is just, it contains the relevant information, but it contains it in a different way than non-arid conditions contained it. And then the model is not interpreting that correctly, right? So it's kind of like, that's a question of causality also maybe is, how do you know which situation you're in? Might have a lot to do with information theory and things like functional performance of your models.
That's an excellent point. Yeah, we were basically basing it on the fact that we tried 3 representational approaches and we got the same pattern in all 3 cases. So that's just like 3 data points, which is better than 1 data point, but it's clearly not definitive. And we can't conclude that that's the problem, but it forms the basis of forming a hypothesis about that being the problem. And so maybe that feeds back to the discovery issue, which is now I can formulate a hypothesis and go out and test it, which would be to go get additional sources of information to add to my data set and see if it makes a difference or not. Of course, that could be self-fulfilling. I completely recognize that. But your point about how do we know that we've tested all the viable representations or we've extracted all relevant information from the data is a really, really, really excellent one. Let me take advantage of that to raise the little example that I've been using to think about this problem of data and information data versus information models, and I'm curious to see what your guys' reaction to this is. It's a very simple example, and it's clearly not complete, but as a basis of conversation. So let's say I make 2 measurements, X and Y, and I give you 2 points, XA, YA.
We are not watching your whiteboard.
Oh, sorry. I was sharing. It's not, sharing is paused. Bring your share window to the front. How do I do that?
Might need to
stop and start again.
Slideshow first.
I never seen that. I never saw that comment before. Now you can see? Yes? Okay. So I've chosen a particular coordinate system, X, Y. I've got 2 data points, XA, YA, and XB, YB. And now the question that I'm trying to answer is, here's X star. What's the value of Y star? And the question is there information in the available data, which is XAYA, this is D, XBYB, so these are co-indexed, 1 and 2. So is there information there which I can use to determine the value of Y star, right? And the claim I'm going to make is that just using the data alone and the representational approach that I've chosen for the data, which is this XY coordinate system, is that there is no information in the data yet. There may be latent information, but there's no explicit information. There's no way for me to extract information from the data alone, which allows you to tell me what the value of Y star is. In other words, I have to impose assumptions on the problem. And in science, we typically impose 2 interesting assumptions. I'm curious if anybody can think about what those 2 are. Right. The value of Y could be anywhere along this line.
Hoshin, I don't know if I understood well your question, but what you're trying to say is that before predicting X star, we should kind of know about the value of predicting X star, right? Or
well, for whatever reason, I want to estimate Y star, and I want to do it using this data set. And the point I'm trying to make here is that I have to impose some representational assumptions on the relationship between X and Y in order to be able to do that. I can't just use it using the data set alone. So the classic assumptions I have to make are that there's a function y is equal to f of x. I have to decide whether that function is deterministic or probabilistic, right? These 2 points could be from a probability distribution, or they could be from a function. And I have to make some assumptions about smoothness and continuity. So this is derivatives and continuity. And the moment I do that, I can postulate some hypothesis about y is equal to f of x. Fair enough? And I could make different assumptions. I could assume it's a straight line, and so on and so forth.
Well, there is isn't there a more basic assumption which is reflected in that y is equal to f of x? Basically, you're saying that x star is generated by the same system as it's generating xa and xb. And therefore, you can write y is equal to f of x. I mean, if xa and xb is coming from one system and x star from another system, then
correct.
They're going to have to assume from.
Yeah, so you're right. I'm assuming that they come from the same data generating process. Yeah, so there's a bunch of assumptions, yeah. And the point I'm trying to make now is I can represent my data xa, ya, xb, yb by a certain number of bits, okay? And I can represent my equation, all of these assumptions, by a certain number of bits. And these could be used as a surrogate for how much information is contained in the data and how much information is contained in my modeling assumptions. And if in order to make a prediction about Y star, I need the information in the bits related to the data, and I need the information in the bits related to the model. And if the number of bits related to the model is larger than the number of bits related to the data, I could reasonably question whether more of the information is coming from the model or is coming from the data. So now we say, okay, so that argues for a minimum description length approach, which means I put the minimum number of bits into my model representation. I make the smallest number of assumptions to try to achieve my goal. And now if I collect more and more and more and more data, I could measure the number of bits required to store the data, and I could measure the number of bits required to represent the model. And at some point I could say that the number of bits required to represent the data far outstrips the amount of data required to represent the model. And so I have a lot of confidence that any decision I make is more determined by the data than by the model, but I can never say it's 100%. And that poses an interesting challenge about the question as to where the information comes from when I make a decision.
May I say something?
Of course.
Yeah, thanks for the graph and the example. And I think I have so many things to say, but I think I got the point. What I want to point out okay, I mean, I think I can argue from philosophical perspective and the mathematical perspective on this issue. So let's just do the mathematical part in the first place. I think the struggle here is the tug of war of representing infinite system using a discrete finite system. Because when you assume this is a real axis, there's an infinite point between xa and xb, and when you break down into bits, you inevitably have to represent this information in such a package that you talk about how much information is rich enough to help you determine that particular point. But no matter how much you do, when you look at infinity, there's no matter how much information you have, there's always no way you can rule out that x star is a singular point because of infinite information order. So that's the mathematical argument I want to raise. And the other one related, because you talk about the smoothness and the continuity, I think that's relates to the human perception about this continuous calculus, mathematics. But real life is not necessarily that. It could be rugged, discrete. That's real life. Because we are happy with the Newtonian mathematics that give a lot of mathematical properties. We hug to it, we love it. We hope the world will be like that, but it's not necessarily. And that's one. That's number two about the philosophical one. I don't know. It's more like, you ask whether it's information. I would say there's always information when you give these 2 points, x, a, and b, to determine x star in between. But the question will be, is there sufficient information to do that? And then that comes to be the quantitative question, which what is the sufficiency? How much information is sufficient? So I think that's more like a philosophical question. So that's going to be my reaction to this.
Nice.
Hoshin, I like your idea. It's pretty convincing to think of it in terms of bits describing processes and how much of that is partitioning between the explanatory power of the model and the data. Regardless if the type of relationship that the data hold, I think is powerful, and that's the beauty of it, because it can explain, even though if the data are not related in some way. Like, for example, if they don't follow the first law of geography, which is data that are close together are alike, it doesn't matter. Because I'm just putting data there. I'm trying to explain how much X star can be predicted from the other data. It can go beyond that law, for example. I like it. Thank you for sharing the idea.
So just to be provocative, Allison, how old is your son now, Carson?
He just turned 2.
Just turned 2. If you give him this question about XAY and XBYB, that is the data point. Okay, you can construct anything, cube and color or something. I mean, I don't know. And then you ask him something in between, X star, what would he predict?
Well, I think you're asking too much of him, but I see where you're going.
My point is this. I mean, over time, our mind is getting trained to think about the world in ways, and we ask those questions in that way. So no matter what model we conceptualize is part of our thinking. We're already imposing things. So when we choose to analyze data, I mean, data by itself is just a bunch of numbers. It doesn't contain any information. We extract information out of that. And in the process of extracting information, we are imposing certain notions on it as to what it means to extract information, right? So a 2-year-old will extract information very differently from a 10-year-old versus somebody who has a PhD and knows of maximum entropy principle. So say, well, XA, YA, XB, YV, X, the maximum entropy estimate is a linear assumption between those two because you cannot impose any further information on it, right? I mean, that's your thing. Now, if you know more, I mean, then you can do better. So our knowledge base guides or provides the lens through which we are filtering this information, data to extract information, right? But the world is evolving in whatever way. And so there is really potentially no way to separate information about data and models. It's just that you're comparing two different models. You are seeing the data from one lens of a model, and you are basically looking at a physical model in a different lens, right? So that's one way to think about it. I mean, I'd like, as I said, I'm being provocative, and so I'd love to get your reaction on that.
No, I think you're absolutely right. And this is why I'm more and more convinced by minimum description length as a guiding principle for everything we do. Because let's say that I don't have 2 data points here, but I collect 1,000. And then I collect 1,000,000. And then I collect 1,000,000,000. At some point, I'm going to run out of storage. And if I have to do a search through all of those data points to figure out what the value of y is for any given value of x, the lion is already going to have eaten me.
Yeah, but Google is doing that. Google is doing that, right? I mean, they're collecting data about everything that is going on in the world at any time with billions of people, and they're still able to sift through that and find something. I don't know.
Sure. If you have the storage and the processing power, yes. But as a human being, I have some limitations, or as an organism, and of course that'll change. But the point being is that I think that we invent continuity. I think that we invent continuity, smoothness, and all these assumptions as part of our dictionary in order to come up with a shorter description length way of representing the data. It's just more efficient and more effective and survival oriented. And so we construct dictionaries and representational rules and so on and so forth. We invent these things. I don't think that they're actually fundamental. I think we do them because we're forced to. And because doing so makes us more more fit for survival, so to speak.
Yeah, I mean, I buy into that concept, but I'm struggling in so many different ways. So I don't know. When I was doing my PhD, I was working with wavelets. They were just coming out at that time as a powerful mathematical technique. And the concept of dictionary was invented to characterize the different wavelets, right? Mm-hmm. So you could choose one of many different basis functions, and each basis function has a certain I don't know, support and frequency extraction. And so Fourier series is one of those dictionaries, sine 1x, sine 2x, and so forth, right? And so we can create these dictionaries in any number of ways, and we can find the minimal representation when mapped onto these dictionaries, right? I mean, these Fourier systems, I mean, wavelets is a Fourier system, it's orthogonal decomposition, which means you can reconstruct the signal to arbitrary high precision, right? So, which means basically you're taking whatever is in this data and you're mapping onto these basis functions, which is your words in the dictionary. And because you can then reconstruct the original signal, then you go and interpret what does this mean when we have 5 sine x plus 2 cos x and so forth. And so does the minimum description length idea in a binary system give us any more advantage as compared to a minimum description representation in a wavelet space or any other orthogonal space. So, and if so, how? If not, then how do I see the world?
So I personally think there are an infinite number of effectively infinite number of equivalent encodings that preserve all the same information. Okay. So I don't think there's a correct one. But some of those encodings are easier to decode using tools that we have available to us, and some of them are much more complicated to decode. So we happen to choose the ones that, we like things to be linear and Gaussian and superposition.
Yeah.
Right? So all of our artificial neural networks, deep learning algorithms, they basically project the data into feature spaces such that you can implement a linear superposition at the end.
Right.
It's a choice.
Yeah.
Well, I want you to sort of follow this argument from the Fourier transform and wavelet analysis. I think, yes, there are different representations, but I think they also depend on what kind of question you want to represent, right? The Fourier transform is beautiful. It's one we started, but also have problems when you look at the functions not so periodic. It got the issues with convergency and many other things. That's where the wavelet came into the picture and got stimulated to find a better representation for certain kind of signals that's not so well represented by the classical Fourier transform representation. So I think in my view is there are different ways to represent, but probably in the particular question space, they probably give me a optimal solution that's or superior compared to others. Even among different wavelet forms, you can always choose someone to represent particular signal much better than others.
So I think what you're saying, Longshen, is that for any particular context, there may be an optimal dictionary. There's a particular dictionary which will be optimal for that particular problem, right?
So, I mean, I think this is a two-way process, right? One is, and I think this goes to the basic notion that Hoshin was trying to present. I missed the presentation, but this idea of representation. So you can ask a question and get it answered well if the representation makes answering that question possible. That's one thing. The other notion is, if there is a new way of representing something, what questions can you ask? So not driven by questions a priori, but a representation a priori, saying, hey, I have this representation and it follows these properties. So the question to ask is, for something to be a representation of a system, what properties should it have? Right? Yes. And then if you know that, then we can figure out whether there is an equivalence in representations, or there are transformations across the representations, and therefore questions asked in one. So the questions you ask in a Fourier domain, you cannot possibly ask in a physical domain or get answered, right? So I think there might be a depth which needs to be explored here in there.
That's very interesting, Praveen, because you're saying that there's an interplay between the representational approach and the question that has to be mediated,
right,
in order to choose or design the representational approach.
I feel the reverse direction is probably harder. If you don't really know, you just somehow come up with a new representation. Normally, new representations appear under certain motivations. That's normally question driven. But if you don't know, somehow just some reason you got new representation, you look into question space, yeah, I think it's new to me, but I think it's probably the harder question than the other way around.
Yeah, but it is done all the time, right? You get a new representation in one field, and suddenly that is easily adopted in another field to ask a question. So wavelet out in a geophysical field, basically from time frequency localization, immediately got into mostly electrical engineering, Mala's development on orthogonal representation. Original wavelet was basically just a continuous transformation, and went into mathematics, and then from there exploded onto any number of issues to address going on to today, right? So I think we see a representation that comes about because of some questions in a field, and then immediately start asking, what can it do for us? Right? I mean, that, so we are going back and forth between these two very quickly. I mean, the information theory, for example, was developed, we all know the history, but not for geophysics, right? But then we suddenly started looking into those questions. So I think that is happening, and it may, I mean, first of all, it happens because we asked an analogous question saying, hey, these guys in one field asked, can I ask a similar question in this field? I mean, that's the first and the low-hanging fruit approach of adoption of a technique. But then very quickly, I think it morphs into very specialized kind of a thing. So I think, yeah, I wouldn't dismiss it that easily. I would be reluctant to do that.
Actually, it sparks the thought that technology and representational approaches are in some sense synonymous. Inventing technology is partly related to inventing representational approaches, or inventing representational approaches is partly related to progress in technology.
Yeah, I don't say thanks for the clarification. I thought it's you mentioned that it's the transfer of knowledge or technology between different field. I was thinking about the original, the original idea people came up with Fourier transform, the original idea of generating the wavelet. So normally that's driven by some mathematical intention or desire. Yeah, I fully agree. The transfer is, yeah, that happened now.
What's interesting is how it changes the way we think about the world, right? Because the moment you think in terms of a signal as being composed of sines and cosines, a superposition of sines and cosines, a superposition of wavelets, it gives you a different way of thinking about reality. And then that leads to new thoughts, potentially. And that's why it explodes and people start adopting it in multiple disciplines, because now they suddenly have a new language, they've added to their dictionary of ways in which to build representations of the world. And so one of the first things that happens in any field is everybody and their grandmother wants to then go out and, well, there are always the people who resist it, but then there are a lot of people who just want to go out and try it, right? And I think I mentioned this before, but I was asked to review a paper some years back where the basic point of the paper by the authors was they tried 3 different machine learning approaches on a data set, and they got 3 different answers. And they wanted to publish that. And I said, I think I could have told you that before you started. More interesting is, why did the 3 different representation approaches give you 3 different answers, right? What were their strengths and weaknesses, right? So that would be a publishable paper, not just that I tried 3 things and they all gave me different answers. I don't learn anything from that. Okay, I learned that they gave me 3 different answers, but you could almost have predicted that from the beginning, right?
Hoshin, if we have some more time, do we have some more time to talk?
I think as long as anybody wants to stay on this call.
I'd like to hear more about the minimum description length that you talk about.
Okay.
I'm intrigued by that. And if that minimum description length refers to a time length, or is it a dimensional length, or if the 2 of them are transferable, or you can change space for time, for example, to describe a process. And if models, for example, can help you reduce that dimensional length in describing a process, or add to understand phenomena and kind of accelerating knowledge before collecting more data, for example. Yeah, I'm
okay.
intrigued.
You buried a lot of questions in there.
Sorry, just tackle one if you want to. Yeah.
Stephen Weiss is arguably our local expert on description length. But let me put it this way. It appears in science that the fundamental way we build representations is using binary. We create the simplest possible alphabet dictionary we can create is 0 and 1. You know, we can think in terms of objects and relationships. We can think in terms of on, off. We can think in terms of yes, no, whatever it is, but that's the simplest one. Now, that doesn't mean that that's the most efficient way to represent information. You can use a decimal system, which uses 0 through 9. Sorry, you can use a 10-base system, which uses 0 through 9. You can use hexadecimal, which uses 16. You can use an alphabet, which has A to Z, 26, and so on and so forth. And Chinese has, I don't know, several hundred characters. I'm not exactly sure. But let's go to the simplest one, which is the binary one. And we build our computers based on a binary representation, a dictionary. And then because that's hard for us to understand and interpret, we build translators, which translate between binary and 10-based or other kinds of things, right? So the idea of minimum description length is that since you can represent anything that can be represented on a computer can be represented as a string of binary numbers. So you can count the number of bits required to represent that thing to some level of precision, right? So if you want to represent a number using 8-bit precision, it has a certain description length. If you want 16-bit precision or 24-bit precision, it has a different length. You have to decide what is the precision you want to do. The moment you do that, you can count the number of bits required to store it. And then if you want to do computation on it, you can count the number of operations and the number of bits required to do those operations, and so on. So the idea of minimum description length is that if everything is thought of as a computation, storage and computation, then minimum description length is the shortest way of representing in terms of bits in order to be able to achieve that storage and computation. And so you would not store the thing with twice as many bits if you could get away with half as many bits, because it requires less computation to process it and store it. That's the way I think of it now. So for example, if you are an Eskimo, you've heard this one, you may have 24 different words for snow. And if you live in Chile or South America, you may only have one or even none if you've never experienced snow, right? So that has to do with the resolution or the degree of precision with which you want to represent some concept. So that becomes pretty powerful because that says you can reduce everything to a bit computation in principle. In practice, how do we know its minimum description length is very, very hard to know, but in practice. So my argument from that is that I get a bunch of data, XA, YA, I get these data, I put them on a scatter plot, and after a while I go, you know what, it's too much work to carry this data around. So instead of representing 1,000 or 100,000 bits, I'm going to create an equation, and that equation I only need 3 or 4 or 10 or 20 bits to store. And I can do computation very quickly on it. I have to create a dictionary which tells me how to do the computation and all that. But that dictionary which tells me how to do it somehow assigns meaning to me. Now I have objects in my mind. And now I have a shorter description, and I can do the computation faster, and so I don't get eaten. And to me, that has very, very huge explanatory power. I'm not claiming it explains everything, but so far, it's like, it's this one view on the world which I'm hanging out with, which I just happen to like at the moment.
Thank you. Yeah.
I can add one more thing to that. So we have things like a Kaiki information criterion and Bayes information criterion and Kashep information criterion, where they count the number of parameters, right? But arguably, you can have two models of completely different complexity, which have exactly the same number of parameters. And so AIC, BIC, and KIC are only useful for comparing between models which have the same degree of complexity. And there was a paper, I think I sent to some of you, where a person showed that you can encode any data set with a single parameter by choosing the correct representational approach. But I mean, it's a trick, but it illustrates the fact that you can bury all the complexity in the equations and make it look like you only need one parameter to answer the question. And the true complexity is actually described by description length, not by number of parameters.
But that equation didn't look very complicated. I was intrigued.
It was intriguing, wasn't it? Yeah, it was a very clever encoding scheme.
I want to play with that at some point in Mathematica because it's pretty easy to do that.
It might be a great way of storing data, right?
Hoshin, this binary notion you just presented, that's basically you talk about in classical world, right? It's not necessarily hold true if you talk about the quantum world, the information representation. Okay.
That's an extremely good point. In the quantum world, you have a different representational approach, and so you have a different dictionary, and the rules are different. And that then allows you to build different kinds of computers. So that's an interesting, yeah, that's a very interesting example. Thank you for pointing that out.
And I guess if we have different dictionaries, then we need a table of content that can help us to navigate through those dictionaries. Otherwise, the information will be lost because we don't know what are we using for in each case.
Yeah, we have definitions, right? So A means that sound, and B means B, that sound, just like ein means one, right? And then we have rules of language, which say, how do I combine letters to make words? And then how do those words get combined to form sentences and longer thoughts? So yeah, there's a whole bunch of rules which have to be encoded. So if you're trying to build an artificial intelligence to understand language, you have to encode all of that stuff. And by the way, I'd like to argue that we started out with numbers, and then we wanted to do addition because we had to solve a problem of storing grain or keeping track of how much grain we had. And then eventually it became so large that we had to invent multiplication as a new representational system. And then we invented logarithms to handle scales. And we kept inventing new and more MDL representations to reduce the amount of work that we had to do to store and compute. So each time we had to add the rules to our dictionary, but we gained because we ended up with a representation that was shorter. And my argument is that machine learning needs to go in the same direction. So right now, everything is based on rectified linear units. But why would you use a rectified linear unit if a logarithmic operation could be represented instead of by 100 rectified linear units by 1 unit with a logarithm, or so on and so forth? You know, we don't need to reinvent the wheel. We already invented these things. And I think Max Tegmark has shown that there's no reason you can't build artificial neural networks that actually learn physics equations which are interpretable by us, because they use these fundamental components as their building blocks instead of just rectified linear units. Well, we've gone more than 2 hours.
Yeah.
It's been fun.
I need to start driving to Chicago, so I'm going to drop out here. Thanks, Hoshin, and sorry for missing your presentation, but I'll catch up.
All right, thank you. As I said, I really appreciate the comments, because I think this question of discovery is just so fascinating. And it's fascinating for many reasons, one of which is it makes us question a lot of things and think about other things that we wouldn't otherwise have thought about.
Yeah, and this is just a parting thing, not for another discussion at this time, is if you look at the history of science, there is a huge number of discoveries that are accidental, in the sense they were not designed for that. They were basically, you go from X-rays to other things. I mean, and so a watchful eye of finding and recognizing the significance of an anomalous outcome has been the foundation for discovery. And at the same time, I mean, theories have been the foundation for discovery, right? I mean, you look at relativity and the number of discoveries that has spawned. So I think it'll be useful to have methods that are tuned for discovery, but I mean, the key thing is to be able to catch an anomaly as something significant rather than dismissing it as an outlier. And that, I think that's where this would come in.
So there's the element of what you expect and what you don't expect.
Right.
And you have to account for both.
Yeah, so there was this very nice quote which says, if the data supports your hypothesis, you have made a measurement. But if it contradicts your hypothesis, then you have made a discovery. And I think there's a lot to be said about that, right? So
supports hypothesis, you're calling that a measurement. Okay,
right.
I like that.
If it contradicts, then you made a discovery.
Okay, I'm going to have to use that one. That's great. I like that. All right, guys, have a good Thanksgiving.
Yeah, everybody.
Thank you. Bye, everybody.
Bye.
I appreciate you taking the time.
Bye-bye. Thanksgiving. Happy Thanksgiving.
Thank you all. Be safe.
You. Bye-bye.
Bye.